Hello, welcome back. In this segment, I will formally define what is a one-way function, which is a key component in cryptography. F is a function from an arbitrary input of arbitrary length to an arbitrary output of arbitrary length. So we don't have any constraints on the input length or output length. That's why I put a star, okay? All right, let's now consider this inverting function experiment. We call it inverting experiment. So an inverting experiment basically is parameterized by n, which is a security parameter. I will give you examples in a moment. Challenger is randomly picking an n-bit number. Let's call that number x, right? And the challenger is going to apply the function f. You have to assume f is known to the world. The function f is not secret. Okay, f is public. So y is nothing but f of x. Okay. The challenger sends to the adversary the value n and y and asks the adversary to break the function f. So adversary will do whatever magic he wants to do with it. We don't know exactly what he's going to do, but for us it's a black box. So the adversary does his magic and returns an x prime. Okay, we say the invert experiment outputs 1 if the value that we got from adversary sends x prime, and if f of x prime is same as f of x, that means the adversary was able to find a collusion, right? That's basically the meaning of this statement. Meaning, suppose you take 2 points here, you have x here and x prime here. Okay, they need not be equal. They can be two distinct points. They both map to y, which is nothing but f of x. Okay, which means the adversary was able to find the pre-image of an element y and was able to find another element which will take it to y. Okay. This is not one function, okay? This is just generic one-way function definition. All right. Now let's define more precisely what is a one-way function. Now that we have defined an experiment, so in one-way function is made of two components. One is easy to compute function f, right? So you should be able to easily compute f by just calling f, and you should get the answer in polynomial time in a length of n. So it should be very quick. That's basically how we define polynomial functions. But on the other hand, it should be difficult to compute f inverse of x. So given y, it should be difficult to find x or any other element that maps to the same y. Okay, that's basically what I have drawn here. Given y, it should be difficult to find the pre-image. Okay, it should be difficult. So what does it mean by difficult? We can formalize it here. The probability that the adversary was successfully able to find x prime, right, is negligible. That's basically what I have formalized it here. Negligible in length of n. Okay, it's a polynomial in n. If n is, say, a 256-bit number, it's the probability that the adversary was able to find an x given y, or not necessarily x, it can be x prime also. It should be negligible in the size of n. Okay, such a function f is called a one-way function. From a theoretical computer science perspective, we don't know whether such one-way functions exist. However, there are some practical one-way functions. We believe they are one-way. For example, factoring, right? Given a composite number, let's say you are given two prime numbers p and q. You multiply them, right? You get a number n. Given n, it's difficult to find p and q. That's basically one way. Multiplication is easy. You can multiply p and q to form n, but given n, it's difficult to go back. That's a classical example of a one-way function. We also have other one-way functions using number theory concepts. For example, the function f of x is equal to say x square mod n, where n is a composite number. This is also considered to be one-way function. Okay, there are many such one-way functions based on number theory concepts, but they are not proved to be one-way functions. They're believed to be one-way functions. Okay. If actually we can prove one-way functions exist, then there's a groundbreaking result that we can show that p is not equal to np, which I will cover later. But at this point, I wanted to show to you that how we define one-way function very formally, right? We have a function f which takes an arbitrary input length and it produces an arbitrary output. That's basically what this function f is. And how we define it is here. It must be easy to compute f. Easy to compute means polynomial time, okay, in the length of the input, and difficult to compute f inverse, okay. And just to be clear, f itself need not be one-to-one function. Okay, the collusions are perfectly fine. You can find two different numbers mapping to same y. The one-way function definition doesn't rule out collusion. Okay. The hash functions are special, right? Hash functions used in practice, they are not variable length inputs. They are fixed length inputs. They map it to fixed length outputs. Okay, at the fine-grained block level. Okay, although you can call hash functions for variable length inputs, at the fine-grained level, hash functions are designed to operate on a particular block length. Okay. All right, so that's basically what I wanted to show to you about one-way functions. Okay, it must be impossible for an adversary to invert the function in polynomial time. That's formalized it here. The adversary finding another number x prime such that f of x prime is equal to y should be negligible. Okay, the meaning the inversion game producing the value 1 should be negligible in n. Okay, n is the security parameter, right? If you choose a n that is too small, then adversary can just try all possible x's, right? And then given y, he will be able to tell the x that that's not what we are interested in. We are interested in n being sufficiently large so that brute forcing is out of question. Okay, that's basically it. Thank you very much.